And here we go. All right, so here is the deal. As always, we wait for Zoom to pop up. And okay, so as always, we are going to start with the calendar spreadsheet, which of course you can get to from the class's announcements, the only announcement, and this is 7th period. So we'll open up the odd sheet. Okay, and today being Tuesday the 2nd, which is an odd day, we're going to do lesson 4 from the current unit, which is called Digital Info, which I should have there. Okay, and with this activity, there are 2 handouts connected with it. We'll give you the other one shortly. The only reason these are linked here is if you are not in class, you will have the ability to print them out and do them so that you can return caught up. All right, show up caught up every time. These activities, the worksheet is due at the end of class. The due date is 90 minutes from now, which might sound rough since you're not even holding the document yet, but trust me, there will be plenty of time. Okay, grading's coming up. I will be grading the green and yellow sheet probably tomorrow. If you have not handed it to me yet, please do so. After I grade it, it is then going to lose 10%, and you have 5 classes to turn it in and complete it, and then that's the deadline. Okay, so what are we doing today? We are going to learn binary, how binary numbers work. Okay, so binary or base 2 is another number system just like base 10 or decimal or regular numbers. Okay, so those are all the same. Binary, decimal, base 10, and regular numbers are all the same thing. And obviously you know those, you know how those work, but we're going to break that down into a very, its lowest level, its most basic form, and that will help you understand where we're going with binary, with base 2. Okay, you don't need to write this yet. This is just for explanation. Okay, so we know that in base 10, if this is where the decimal is, the first column is the ones column. The second column is the tens column. The third column is the 100th column, and so on. The fourth column is the 1000s column, and so on. If you have a number like 4,308, you have a 4 in the 1000s column, so you get 4,000 for that. Okay, you have a 3 in the 100s column, which means you get 300 for that. I have a 0 in the tens column, so I get no more, and I have an 8 in the ones column, so I get 8 more. 400 plus 300 plus 8 is 4,000 plus 300 plus 8, 4,308. Okay, that shouldn't be anything new. But how do we get these column values? That is the key. Of course, this is base 10. The first column is 10 to the 0th. 10 to the 0th is 1. And 0 is the ordinal, or 0th is the ordinal for 0. But we'll work with that. 10 to the 0th is 1. 10 to the 1st is 10. 10 squared is 100. 10 cubed is 1,000, and so on. It is base 10. The base of the exponent is 10. Every time you move over a column to the left, every time you increase a place value, it increases by 10 times. It is 10 times bigger than the one before. 10 to the 4th is 10 times bigger than 10 to the 3rd. Yeah. And so that is base 10. This is where our number system comes from. This is how it works. Now, we are going to convert or adapt this to binary. So you can write along as I write aloud, as I write up here. Okay, so in binary, the first column is, of course, going to be the 2 to the 0ths. What is 2 to the 0? 1. Anything to the 0th is 1. Okay, next column, 2 to the 1st. What is 2 to the 1st? itself. Yes. Okay, you can go ahead and fill this in as I fill it in. This is y'all. Okay. Following 2 squared. What's 2 squared? 4. Maybe you'll see a pattern here. What's 2 cubed? 8. Okay. From here, you should be able to fill in the rest, even without any understanding of binary yet, which this is only, your first step into binary. Okay. So of course it goes 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th, which are 8, 16, 8, 16, 32, and so forth. Okay. Those are the columns. The next thing I want you to do is in this bottom row that's full, the row below that, put all zeros. Just go ahead and fill it across with some nice, neat zeros. Okay, once you have 8 zeros across, I want you to fold the tabs that have been painstakingly cut from down to cover up that 0. Okay, I tried very hard. Well, I tried medium hard to make it look nice and cut on the lines, just to save you all the time of trying to find scissors and stuff. So you may need to adjust the slash, but I want you to fold each of those tabs up so that it covers the 0. And when the tab is folded up, on the back of the tab, well, the face that's facing you once it's folded up, I want you to put a 1 on the back of each of them. And all the way down. So each 0 could be covered up by a tab, and when it's covered up, there's a 1. Okie dokie. All right, so let's figure out how to do some conversions. Okay, we're going to start with just a 4-bit number, meaning the first 4 bits. Okay, a 4-bit number. And when you say a 4-bit number or 8-bit number, it's like saying in regular numbers, oh, the price was a 7-digit number. You know its range. You know how many place values it has. That's the case. 4 bits versus 8 bits would be all the way across. 8 bits is a very common chunk size. We'll talk about that later. Okay, so if we have the binary number, let's say you get the binary number 1001. You don't need to write this yet. Okay, if you have, we're doing just a 4-bit number, that means this first bit over here gets covered up. And so you have a 1 there. That's this first one. The second one is a 0. The third one is a 0. And the last one gets covered up, and it's a 1. Okay, so every place you have a 1, you add together all the numbers of that place value. So I have a 1 here, which means I get 8. I have a 0 here, which means I get 0 for here. I have a 0 in the 2's column, and I have a 1 in the 1's column. 8 plus 0 plus 0 plus 1 is 9. And I can pick better colors or write neater. Okay, so in decimal, this is how you write 9. In binary, this is how you write 9. Now, you need to understand, and I could probably write this neater, you need to understand the concept that this, let me neaten it up, 1001 is 9. It's not 9 in binary. I mean, it is 9 in binary, but it's not 9 converted to binary. It is 9. Just like this is, let's pick another color. This is 9, and so is this. It's just like translating a word into another language. It isn't less a it doesn't, it isn't less than the one that it came from. It is that, just in another language. Both of those are 9. It's just another way to write it. Okay, so that is binary to decimal. Any place you have a 1, you add up, you get that value, and you end up adding all the values of the ones that have 1 below it and add them together. And that's the total. And that is binary to decimal, addition. Binary to decimal is addition. Okay, decimal to binary is subtraction. Okay, let's say we want the number 37. Okay, this is how you write 37 in decimal. You should know that. How do we write 37 in binary? Okay, this is the method. Start with the value of the leftmost column and ask, can it fit into our number? Okay, can 128 fit into 37? It cannot. It gets a 0. Can 64 fit into 37? It cannot. It gets a 0. Can 32 fit into 37? It can. It gets a 1. And then we subtract 32, which leaves us with 5. Our new number is 5. We could forget about the fact that it used to be 37 and we had a 32. It's just 5 is our new number. Continuing on. Can 16 fit into 5? It cannot. Can 8 fit into 5? It cannot. Can 4 fit into 5? It can. And since we got a 4, we're going to subtract 4. Our new number is 1. Okay. Now, can 2 fit into 1? It cannot. Can 1 fit into 1? It can. Okay. And we subtract 1 and our number is 0. Obviously, we made it to the end and we needed 1, so 1 ended it. But if at any point you subtract the number and it gets you to 0, that's it. Okay. If this was 38, we would have had, and this is just, if it was 38 and we subtracted 32, we would have had 6. We subtracted 4, we would have had 2. And then we would have had the 2, this digit. 2 minus 2 would leave 0. And when we got to here, we would already be at 0. So it's just whenever you run to 0, that is the case. Okay, so now a couple of idiosyncrasies of binary to sort of help understand how it's working and help you solve problems and sort of make big leaps and shortcuts in solving problems. All right, so if you have, we'll just work with a 4-bit number, which means these bits. Okay, if you have a 4-bit number, what is the lowest number you can make with 4 bits? All zeros. What is all zeros? 0. Okay, the lowest number you can make with 4 bits is 0. What's the highest number you can make with 4 bits? The highest number you can make is all ones. What is the value of all ones? Well, it's 8 plus 4 plus 2 plus 1, which is what? 15. 15. Okay, this is supposed to be the easy part. Okay. Thank you. Okay, 8 plus 4 plus 2 plus 1 is 15. Notice the value of the next column. The value of the next column is going to be 1 more than the highest number you can make with however many bits. Okay, but also, yes, you can make, if you only have 4 bits, you can make up to the number 15. 15 is the largest number you can make with 4 bits. But the important concept is that you can make 16 different numbers. With 4 bits, you can make from 0 to 15, which is 16 different numbers. We give a lot more value to 0 in computer science. We always count from 0. It is its own place. Okay, so you can make 0 to 15 with 4 bits, okay, and the next column is going to be 1 more than however many, the next column will be 1 more than that number, or all ones will be, another way of saying it, 1 less than the next column. Okay, what is the value of 8 ones? Well, you could do 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, or I can, hold on a second. No, it is not 2/3. Okay, so what would the next column be? What would this column be? The next column would be the 256's column. So what is the value of 8 ones? 255. If you've ever seen in any sort of computer software the number 255, it's not an accident. It's because that value is stored in 8 bits. Okay, most commonly, you will see anything with RGB color, graphic design, whatever. You'll see the red channel 0 to 255. You'll see the green channel 0 to 255, and you'll see the blue channel 0 to 255 because each of those colors has 8 bits of data or 8 bits of storage to keep track of that value. Okay, and let's see, what are some other characteristics? All right, so if I had a binary number that was 1 0 0 1 1 0 1 1 0 1 1 1 0 1, is that an even or an odd number? It's an odd number. How do you know? Exactly. If you add an even plus 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 blah, 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 plus 1, it's going to be odd. If the last number is a 0, it's going to be even. Okay, that is just a sort of a quirk of the way it's set up, but it also, well, I mean, you could say it's the same for decimal. If the last number is odd, it's odd. If the last number is even, it's even, which is the case here. One is odd, and we count 0 as even though we don't teach it that way. Okay, so there is that. I'm positive I'll think of other things as we go. Okay, so right now, you all need a blue worksheet. Okay, if y'all could grab one, everyone needs a single worksheet. And name, date, and period at the top. First and last name, please. There could be more than one George. Okay, so, here's the thing. Of course, I thought of something after the fact, but it relates to everything. All right, so the relevance of having a graphic whatever thing that looks like an analog odometer becomes less and less relevant as every car odometer is now digital. But as soon as you hit run here, you probably can figure out what's going on. Okay, in decimal, the base 10 normal, the ones column goes from 0 to 9, and every time it gets back to 0, the next one goes up by 1, and so on. I mean, it's an odometer. You can figure out how it goes. Okay, but the decimal is similar and different from the standpoint, the binary. Okay, it's the same in that the ones column goes from 0 to 1, but then it has to go back to 0. And just like with decimal, every time it goes back to 0, the next column gets incremented. Increment just means go up by 1. Okay, and so that one goes from 0 to 1. When it goes back to 0, the next column is incremented. So it goes from 0 to 1. When it goes back to 0, the next column is incremented. Okay, so it will look like this, with the thing that I said before about 15 being the largest number that you can make with 4 bits. The largest number with any number of bits is all ones. If you increment it, then the next number is 16. 16 is a 1 with 4 zeros. Okay, it rolls over like that, is how you would call it. Okay, so the blue sheet that you're holding with the name, date, and period at the top of yours that you just wrote on there. Okay, so you have to, well, this is technically decimal to binary, even though they didn't fill in. The right column for each is 0 through 7, and then 8. 1, 2, 3. I know all the numbers, I promise. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, and 0 to 7, and then 8 through 15. I'm going to do this in a spreadsheet so that it's neat. Okay, now what I want you to do, this is actually the decimal to binary, which is the subtraction, sort of. Although you could probably piece together, once you see how it works, you'll probably see a pattern. Come up with the binary for each of these values. The 4-bit binary for each of these decimal values. You may work together, you may collaborate, but of course everyone hands in their own work. Okay, ready, go. Of course we will go over it, but I want you to try now. listen up for a second. Yes, and grab some. We'll go over your questions. Okay, so let me give you a little bit of a head start so you know what we're talking about. All right, so our numbers, these are okay. So if your number is 0, that's on the blue sheet, all zeros. Okay, how do you make a 1? You just need a single 1 to make a 1. How do you make a 2? You just need a 2 to make 2. How do you get to 3 using only 8, 4, 2, and 1? 3 is a 2 plus a 1. How do you get to 4? I just need a single 4 to get to 4. How do I get to 5? Well, a 5 is a 4 and a 1. 6 is a 4 and a 2. 7 is a 4, a 2, and a 1. Okay? You're adding, you want to use some combination of 1, 2, 4, and 8 that add up to that number. Okay? A 9 is an 8 and a 1 is 9, and so on. Okay? I'll give you a couple more minutes to fill in the other part or the rest of this first part of the blue sheet. All right, so 8. 8 is obviously just an 8. Okay, how do you get to 10? I did 9. How do you get to 10? A 10 is an 8 and a 2. Okay, 11 is an 8, a 2, and a 1. 12 is an 8 and a 4. 13 is an 8, a 4, and a 1. And 14 is an 8, a 4, and a 2. And 15 is an 8, a 4, a 2, and a 1. Okay, there are your 15 basic, your first 16 decimal numbers. So like that. Your first 16 decimal numbers in 4-bit binary. Thank you. Okay, second part. What do you notice to compare the odd numbers to even numbers? We went over that 2 seconds ago. Okay, or you could just infer based on what you've just done. Okay, second part, binaries with exactly one, with exactly a single 1 in them. Okay, complete the chart with all 8-bit binaries that have exactly 1. We've done the first 2 for you. Okay, so this is, let's go like this. Okay, the first one they have is all zeros except a 1 in the ones column. That's equal to 1. Okay, the next one is all zeros except a 1 in the 2 column, which is 2. Those are the ones they've given you. The next one is 8 bits with all zeros except a 1 in the 4s column. What is that? Well, question mark. And then the next one is all zeros except 1 in the other one. Okay, and keep going. Just so I'm putting this up there, I think it's kind of a little confusing if they don't have enough examples of what they mean by 1, 1. But these are the 8 different ways you can have 1, 1, have a 1, a single numeral 1. And what are those each worth? Okay, this really should be kind of easy. If it's not easy, you're not there yet, but shortly it will become easy. All right, so this one should be super easy. Okay, I mean, you could fill it out here in 2 seconds. The 8 different ways that there could be a single 1 in an 8-bit number are these, and the values are all just the value of that column. Because that's all you get. You get 1 of the value of whatever column it's in. Okay, so this is the next part, or this part right here. Okay, what did you notice about decimal equivalents above? I mean, these questions of like, what did you notice? I guess they're good, but you can really just answer it by saying what it is. Like, I don't know how else to explain what do you notice. Okay, so top of the back, we have some binaries going to decimal and decimals going to binaries. A hint is that you might need more than 8 bits to answer some of them. Okay, so ready, steady, go. Collaborate. Collaboration is encouraged, sure. Okay, so on the back, starting on the left, binary of 1, 0, 0. Super easy. We get a 4, and that's it. It's 4. Next one, we get a 4 and a 1. That's 5. Here we get an 8, a 4, and a 1, which is 13. Okay, here we get a bunch of 1s, which you could add 32, 16, 8, 4, 2, and 1. Or you could remember that any binary number that's all 1s equals 1 less than the value of the next column. If this is the 64, if this is the 32s column, that means 5 1s is equal to 31. It is 1 less than the value of whatever the next column would be. Okay, and the next one is the next column. A 1 in the 64, a 1 in the 32s column, and nothing else is 32. Okay, this one a little trickier, but we've got a 128, a 32, an 8, and a 4. Excuse me, an 8 and a 2, so that's 10. Let's just do this. 128. 128, 30, 170. My brain's broken. Hold on, I'll do this quiet. Shh. I'll figure it out. 128, 130, 160, 168, and 170. Is that what you all got? It's a long day. Okay, and then this one, all 1s, is going to be 1 less than whatever the next column is. The next column, we know our 8-bit Flippy-Doo goes up to the 128s column. That means this is the 256s column, and all 1s is 1 less than the value of the next column. So this is going to be 255, as we showed before. Okay, decimal to binary is a little trickier. It's harder to do in your head, or it's harder for me to do in my head, without some shortcuts. But 5 is just a 4 and a 1, so a 4 and a 1. 17 is a 16 and a 1, so we have a 1 in the 1s, 0, 2, 0, 4, 0, 8, and a 16. A 16 and a 1, a 17. 63 is 1 less than 64. We know the 64s column is the 6th one, so this is going to be 5 1s. Okay, a 1 in the 32s, a 1 in the 16. 6 1s. Yes, 6 1s, the 32s column. So 6 1s. This last one is the 32s column. The next column is the 64s column. It's 1 less than the value of the next column. Hold on a second, folks. Thank you. 64 is just a 1 in the 64s column. If it makes it easier, you can do it in 8-bit, like an 8-bit chunk. I don't know if that makes it easier to see what's going on. Anytime you would be using these in real life, you need to have the leading zeros, not like regular math, but because anytime a binary number is being used, it's expecting that many bits. In this case, 8 bits, it would be sending zeros for leading zeros. Okay. 127 is 1 less than the 128s column. This is the 128s column. So 127 would be a 0. And the rest 1s. Hey, y'all. Okay, so we have 127 is a 1 less than the value of the 128s. So it's all 1s except a 0 at the beginning. 256, we know that 8 ones is 255 because the next column is the 256's column. So 256 is 1, and then 8 zeros. This has to be a 9-bit number. You cannot fit 256 in 8 bits. It would roll over. It would roll over, and that will be a hint for next time. And 513, well, we know the 8th bit is the 128s. The 9th bit, if you had one, would be the 256s. The 10th bit would be the what? The 512s. In order to get to 513, you would get a 512. And no, none of those, none of those, none of those, none of those. Four more zeros and 3 more, and 1. That would be 512. Okay, you would need 10 bits, and the first and last bit would be 1. There you go with 2, 3. What number are we looking at? 513. Okay, some wrap-up questions for you. A couple, I don't know, a complete... Back here on the blue sheet, when you add a 0 to the right of decimal number, it multiplies it by 10. For example, 15 becomes 150. What similar result happens to the value of a binary number when you add a 0 to the right? For example, 11 becomes 110. What is happening to those values? I'll give you a hint. Convert those to decimal, and it will make a little more sense. Okay, do the binary numbers 0011 and 000011 have the same or different values? Explain. Okay, would 2 bits be enough to assign a unique binary number to each vowel in the English language? Doesn't matter if you count Y, the answer is still the same. And the letter Y, not WHY. And how many bits would you need if you wanted to count up to the decimal number 1000? Okay, so that is one part of the wrap-up. The other part of the wrap-up is the checks for understanding, which are available in the place that is loading right now. What period is this? 7. And we go there, and we go like that. Okay, so when you're done with this, of course, I'll take it. But in the what's it called? Code.org lesson. Okay, the easiest way to get to this is, of course, the calendar spreadsheet. Just clicking on the link and going directly to the unit. And for this one, we just need the short answer, or they're not all short answers. Some of them are multiple choice. I think I have them here. Okay, so okay, so for the F-O-U-R, the 4 check for understandings from lesson 4. Okay, first one, multiple choice. 2 schools are merging and adapt to the increased size of the student body. The school is changing system for keeping track of student IDs from a system that uses a 4-bit binary number to an 8-bit binary number. Okay, that's another thing. 8 bits is 1 byte. That's just a thing you have to know. Okay, they're switching from 4 bits to 8 bits. Which of the following best describes what effect this change will have? Okay, increasing the number of whatever by how much? You have to decide which one it is. Okay, bubble 2, reflecting. Each time we add another bit, what happens to the amount of numbers we can make? Okay, you need to pay attention to things like the amount of numbers we can make, how many different numbers we can make, rather than what's the highest number we can make. But regardless, this is very similar to adding another digit in a decimal number. Okay, bubble 3. Okay, how many bits would you need to count all the students in class today? I don't know, go with 30 maybe. I don't know. Come up with the value. And the key is how many bits, not what the bits are, how large of a number would you need in order to contain that number? And the last one, what are the similarities and differences between binary and decimal system? Okay. If for last time, for lesson 3, you did not do the check for understanding from lesson 3, which I told you might make sense to wait. Now is the time you're waiting for. Okay. The check for understanding from last time, which is still on time. How would you explain a number system to someone who has never seen numbers before? Okay. Part of this is the fact that last time we started with circle, triangle, square, or circle, square, circle, triangle, square, to get you to think about numbers differently. They don't have to be numerals. Well, I mean, kind of. But the idea of thinking about the way numbers work without thinking about numbers was the point of that, if that makes any sense. Regardless, do your best to answer it. Are there any questions? Great. This is all due today. I will I'll take the blue sheet when you are finished with it before you leave. And if you have any questions, let me know. Okay? Good work. Proceed.